Right, welcome everyone to session number 2 for the DB2 stream on day 3 of the virtual conference for GS UK this year. I'm very pleased to introduce my co-chair for DB2 stream, Marcus Davidge, who's from BMC Software, and he always chooses really good titles for sessions, and this one's no exception. So marks out of 10 for the claims, drains and automobiles title. And it's all about how DB2 keeps order in a chaotic world. Please put your questions into the chat if you have some along the way, and we'll try and take them as we go. Otherwise, over to you, Marcus.
Well, thank you very much, Colin. Yeah, I shan't say any more about that because Colin said it all. This is session 9.0. As Colin said, I'm his co-partner. I'm a co-chair of the UK DB2 user group and the GS DB2 working group stream. So if I can, this isn't working. Oh. There we go. Right. If I can give a shameless plug for the UK DB2 user group, we have a LinkedIn group, we have a Slack channel, and we have an iDoug page. Please scan and join up and join the conversation. We want this to be a continuing conversation where we can just help each other out. If you're in the UK, I know London has a DB2 user group, Scotland has a DB2 user group, UK has a DB2 user group, and this is it. So please scan, join in the conversation, post stuff, be social, and we will advertise any meetings and meetups that we have as they appear. So the agenda is pretty much this. It's as messy as my thought processes, to be honest. We'll be talking about processes, locks, latches, tables, applications, storage, troubleshooting, isolation levels, claims, drains, locks and latches, all sorts. Yeah, and thanks, Dylan. Yeah, I actually haven't got my hat on because I'm inside. I mean, what kind of person wears a hat inside? I could have taken this out into the garden because it's a beautiful day here. So what are we talking about? So picture a bustling metropolis, thousands of people crossing streets, driving cars, getting to work. It will be chaos without traffic lights, police officers, or bylaws. In DB2 for ZOS, that metropolis is your data. It's your transactions. It's your utilities that are running. It's your queries, your units of work. And in this world, claims, drains, locks, and latches are the silent traffic controllers keeping the peace. So a claim is basically who has access to what. Without a claim, you get mayhem. A drain is basically how do we make sure the road is clear? Without them, you get gridlock. A lock is can two people update this at once? Without them, you get data corruption. And a latch is can we safely manage control structures? So without them, your subsystem crashes. So let's break these down and make sense of how they work and why they matter. Just as an aside, this presentation I delivered a couple of weeks ago to the Waves GS, basically the 101, 102 stream for the GS UK. So it's more of a conceptual presentation rather than deep technical stuff. There will be deep technical stuff now and again, just as an illustration on how this works, but it's more of an overview. So let's break these down. So a claim is basically a DIBS or a BAGSI. It's a mechanism that controls access intent on a physical page set. So who uses a claim or who generates a claim? Some database utilities, some DB2 commands, and some SQL. Where does it happen? Well, it happens to DB2 objects that have an associated underlying VSAM dataset, like non-partition table space, data partitions, non-partition indexes, or index partitions. So what is a claim? It's basically a counter held in storage somewhere, DBM1 address space. It indicates an interest in a page set or a partition. If you want to find out really more technical detail, just take a look at John Campbell's presentation that he gave on Tuesday. It's independent of transaction locks, and it prevents drains until a claim is released. When does a claim occur? Well, it occurs within a unit of work upon the first access of an object and until the next commit point. A claim, unlike a transaction lock, a claim normally doesn't persist past a commit point. To access the object in the next unit of work, the application must make a new claim. A claim indicates activity on or interest in a particular page set or partition, and it prevents claims and drains from occurring until it's released. So the different classes you have here is a write claim class. The actions allowed on a write claim class are reading, updating, inserting, and deleting. You have a repeatable read claim class, which only allows reading with repeatable read isolation levels, or a cursor stability read, which is reading only with read stability, cursor stability, or uncommitted read isolation levels. Excuse me. DB2 generates a trace record for each time period, that a task holds an uncommitted read claim. The value of the long-running reader field, or LRDR THLD subsystem parameter, controls the length of the time period. DB2 also issues a warning message when a trace record is written, and I'm sure we've all seen something like this. So going back to our Metropolis analogy, a claim comes into play when a road needs digging up or relaying. Having pedestrians or traffic meandering up and down while pneumatic drills are in operation or molten tar is being poured doesn't bode well for the road or for the user. So all SQL DML plus both copy and run stats running as share level change are all claimers. So a drain, let's move over to drains. Imagine your table space is a cafe. The owner wants to close up and clean the cafe. For example, you do a reorg. The current customers need to finish up and leave. No more customers are allowed in, but once the cafe is empty, the work begins. So the owner puts up a closed sign on the cafe door to stop anyone else from coming in. All other utilities and commands are drainers. So if a claim indicates activity in a DB2 page set or partition, taking access of objects within a unit of work and releasing them at the next commit point until an existing claim is released, that can prevent a drain from being obtained. So a drain then takes control or access of a DB2 object by preventing new claims and waiting for existing claims to be released. So, for example, a check index needs to drain writers from an index space and its associated table space. A recover, however, must drain all claim classes from its table space. A reorg, depending on the parameters you use, can drain either writers with the drain writers option, or all claim classes with the drain all option. So you've got horses for courses. So what's a drain lock? A drain lock prevents conflicting processes from claiming or draining the same object at the same time. It also prevents new claimers from accessing an object while a drainer has control of it. The types of drain locks correspond to the following claim classes: write, repeatable read, and cursor stability read. So to drain an object, a drainer first acquires one or more drain locks on the object, one for each claim class that it needs to drain. One for write, one for repeatable read, and one for cursor stability. When the locks are in place, the drainer can begin after all processes with claims on the object have released their claims. When the claimer gets the drain lock, it makes the claim and releases the lock before beginning its processing. So let's see how it all works together. We have a simple example where multiple applications, application A in red and application B in green. I do apologize if you suffer from color blindness, because they would be quite indistinguishable, but let me know and I'll change it. They're both working in the same DB2 subsystem, and they're both interested by the same table space. Application A requests a claim to update the DB2 object, say it's using a load. Since there is no existing claim or drain on the object, application A gets the claim. Application A then drains the object. Application B is processing without any need to access the DB2 object at this time. While application A updates the DB2 table space, it's now time for application B to get access to the DB2 object. So at this time, application B requests a claim. A holds the drain on the DB2 table space, so B cannot get the claim. It waits. Waits for claim. When application A finishes with the updates and starts to release the drain, application B is still waiting for the claim to be obtained. Once application A releases the claim, application B is then able to obtain the claim. Once application B has the claim, it can successfully drain the DB2 object and update as needed. Once it completes its processing, the drain is released, followed by the claim, and ta-da, everybody's happy and running independently and merrily. So a lock is basically a hands-off. Oop, sorry, that was drains. Yep, just a sec. A lock is basically a hands-off. They prevent concurrent transactions from corrupting data. They ensure consistency across and within transactions and guarantee data integrity. The important properties to understand locking are their size, the duration, and their mode or type. What is also important is the compatibility between locks. So the size describes the amount of data that is controlled by the lock. The duration is the length of time the lock is held. This varies according to the lock. This varies according to the size of the lock and when the lock is acquired and released. The mode of a lock tells what access to the locked object is permitted by the lock owner and to any other interested concurrent part processes. So let's have a look at the size of a lock. So the highest, the largest size is the DB2 table space, followed by the table, followed by the page or the row, that's the same level. You also have LOB table space and XML table space locks and LOB or XML locks. We won't be covering those. And then we can drill down to partition table space and universal table spaces. They have a whole table space lock, partition lock, or page or row lock within a partition. When you use a page or a row lock instead of a table or table space lock, it has the following effects. Concurrency usually improves, meaning better response times and higher throughput for many users. The processing time and use of storage increases. This is especially evident with batch processes that scan or update a large number of rows. So if you're updating a large number of rows, you're going to be taking a large number of locks, which require a larger amount of storage. Using only a table lock or a table space lock has the following effects. The processing time and storage use is reduced because you're taking fewer locks. But concurrency is also reduced, meaning longer response times for users, but better throughput for one user. It's a trade-off, like everything else. So let's jump back to my little AI-generated analogies. Imagine your table space as a library. With a table space level lock, you would be the only one allowed in. Everyone else would have to wait outside for you to finish reading your book. A table space level lock takes very little time, CPU, and storage. The storage comes out of the RLM. For low usage or small table spaces, it would be fine. But for large, busy table spaces, that would severely impact your other users. They would have to wait for you to finish. So what's a page level lock? So imagine your table space is a library. Everyone is allowed in, but no one else can use your desk while you're using it. Basically, and I'm saying basically a lot, so stop. If there are any other books on the desk or any other rows on your page, when you lock a page, you're stopping anyone else from using those rows, even if you're not interested in the rows that they are, but they're using the same page. So what's a row level lock? Once again, your table space is a library. Everyone is allowed in, and everyone is allowed a book. That's great. Everybody can do whatever they want, but the downside, as I mentioned before, is cost and performance. So what are lock modes? The mode of a lock tells what access to the locked object is permitted to the lock owner and to any concurrent processes. So DB2 uses lock modes to determine whether one lock is compatible with another. Some lock modes do not exclude all other users. For example, assume that application A holds a lock on a table space that process B also wants to access. DB2 requests, on behalf of process B, a lock of some particular mode. If the mode of the lock for A permits the lock requested by process B, the modes of the two locks are said to be compatible. However, if the two locks are not compatible, process B cannot proceed. It must wait until A releases its locks, and then all other incompatible existing locks are also released. So let's have a brief look. I am going to be skipping through this quite quickly because there is a lot of it and everything's in the manual anyway. So we have 3 lock modes for page and row locks. We have a share lock, an update lock, and an exclusive lock. With a share lock, the lock owner and any concurrent processes can read but not change the locked process or row, a locked page or row. Concurrent processes can acquire S, share locks, or U, update locks on the page or row, or might read data without acquiring a page or row lock. Only one U lock can be acquired concurrently with one or more S lock. Now the rules for an update lock. The lock owner can read but not change the locked page or row. Concurrent processes can acquire S locks or might read data without acquiring a page or row lock, but no concurrent process can acquire a U lock. The U locks reduce the chance of deadlocks when a lock owner is reading a page or row to determine whether to change it. The owner can start with the U lock and then promote the lock to an X lock to change the page or row. With an X lock, the lock owner can read or change the locked page or row. Any concurrent processes cannot acquire SU or X locks on the page or row. However, concurrent processes such as those processes bound with current data no or isolation UR, or bind options or running with eval unc yes subsystem parameter and ZPARM, can read the data without acquiring a page or row lock, sorry. So here's your compatibility matrix. It shows the compatibility of the different locks for a page or row lock. So let's move up a scale and talk about partition or table space lock modes. So this is higher and it's more complex. When a page or row is locked, the table, partition, or table space that contains it is also locked in one form or another. This intent lock indicates the plan the application process has for accessing the data. In that case, the table, partition, or table space lock has one of the intent modes, either IS for intent share, IX for intent exclusive, or SIX for share with intent exclusive. So what's an IS lock? The lock owner can read data in the table, partition, or table space, but not change it. Concurrent processes can both read and change the data. The lock owner might acquire a page or row lock on any data it reads. So remember, these are partition or table space lock modes. With an IX, the lock owner and current processes can read and change data in the table, partition, or table space. The lock owner might acquire a page or row lock of any data it reads. It must acquire one on any data it changes. A share lock. The lock owner and any concurrent processes can read but not change data in the table, partition, or table space. The lock owner does not need page or row locks on data it reads. With an update lock, the owner can read but not change the lock data. However, the owner can promote the lock to an X lock and then change the data. Any processes concurrent with the U lock can acquire S locks and read the data, but no concurrent processes can acquire a U lock. The lock owner does not need page or row locks. With a shared with intent exclusive lock, the lock owner can read and change the data. Lock processes can read data in the table, but not change it. Only when the lock owner changes data does it acquire a page or row lock. And finally, With an exclusive lock, the owner can read or change data in the table. A concurrent process can access the data if it runs with UR, and the lock owner does not need a page or row lock. And here's your bigger, deeper, more complex compatibility matrix. So I mentioned the concept of isolation levels. I'm sure you all know this already, but we have 4 isolation levels: cursor stability, uncommitted read, read stability, and repeatable read. Cursor stability is the option to allow maximum concurrency with data integrity. A transaction holds locks only on its uncommitted changes and on the current row of each of its cursors. That's as granular as you're going to get. Uncommitted read allows an application to read while acquiring few locks at the risk of reading uncommitted data. UR isolation applies only to the following read-only operations: select, select into, or fetch from a read-only result table. You're reading through locks, so somebody else might be updating a row or a page. You're reading potentially changed data, and the writer may back out at a later stage, in which case your business logic was dependent upon data that might not exist anymore. So you must make that decision on whether that is going to affect your business logic. Read stability. This operation enables an application to read the same pages more than once and prevents updates or deletes to qualifying rows by other processes, sorry. However, other applications can insert or update rows that it did not satisfy the search condition of the original application. Finally, repeatable read is the least granular option. It allows the application to read the same pages or rows more than once without allowing any update, insert, or delete operations by other processes. All accessed rows or pages are locked, even if they don't satisfy the predicate. Under isolation RR, the data that an application references cannot be updated by any other application before the application reaches a commit point. So basically, you touch it, you got it, and nobody else can update it. So basically, a DB2 lock-in, a DB2 lock-in strategy ensures that no one can read a book, back to our library analogy, that someone else is about to update or delete. No one scribbles notes in the margins of a book that somebody else is reading. That's just rude. An uncommitted read is a little bit creepy. She might change her mind. The reader reads through any locks that are taken to get at the writer's data. But if the writer backs out any changes rather than committing it, the reader has read the wrong data. So how do we implement locking avoidance and locking strategies? Well, first of all, with the bind, there are isolation levels, there are release options, current data options. So let's have a look at the release option. So in your bind parameter, you can have release deallocate. This provides an opportunity for better performance for many applications, but worse concurrency. Release commit allows greater concurrency, but higher CPU time. Isolation level, cursor stability, uncommitted read, read stability, repeatable read, I've just covered. Current data So with isolation CS and current data no, this enables DB2 to release locks early and avoid taking locks in many cases. With current data yes, it reduces the risk of non-current data being returned to the application, but this is a trade-off as it provides a reduced availability for multiple applications to access the same data concurrently. Current data no typically enables DB2 to acquire the fewest number of locks for better lock avoidance. Concurrent access resolution. Somebody had a whale of a time typing this one out when they invented it. You can reduce lock contention that results from uncommitted and insert and delete operations by enabling transactions that read data to access the currently committed data rather than waiting for the uncommitted changes to be resolved. So transactions that read data can avoid waiting for the operations to commit by reading the currently committed data. The option currently committed data means that the data as it was last committed before the uncommitted change that holds the lock on the row. So this is basically a faster operation. For uncommitted delete operations, a transaction reads the uncommitted deleted rows as if the delete operation did not happen. Transactions must always wait for uncommitted update operations. Currently committed data access is available only for data in universal table spaces, which we all have now, haven't we? And it applies only to row level and page level locks. So this is a nice little addition for speed and concurrency and lock avoidance. I just wished they'd chosen shorter keywords than concurrent access resolution, use currently committed, or concurrent access resolution, wait for outcome. How do you implement locking avoidance in your SQL? First of all, you can shouldn't use lob because, yeah, lob means throw, chuck. You can use lock table in your application program as a one-off. So before your unit of work, or at the beginning of your unit of work, you can just say lock table X with, or partition N in share or exclusive mode. You're basically saying, I want all of this. Where does it go? You can add with UR, CS, RS, or RR in your select statements. So that overrides what the package says. You can say, okay, I want this statement to be with UR. I want to read through any locks that anybody's taking. Or you can stick it in your create table space syntax with the lock max or lock size parameters. So in your create or alter DDL, the lock max specifies the maximum number of page or row locks an application process can hold simultaneously in the table space. If a program requests more than that number, locks are escalated. I shall go on to that in a minute. The page or row locks are released, and the intent lock on the table space is promoted to an S or an X mode. If the lock size is table space, lock max must be omitted or its operand must be 0. And the lock size parameter specifies the size of the locks used within the table space, and in some cases also the threshold at which lock escalation occurs. So that could be any table space, page, or row. So let's have a look at some issues regarding locking. We'll talk about lock promotion, lock escalation, suspension, timeouts, and deadlocks. So promotion. A lock promotion is the action of exchanging one lock on a resource for a more restrictive lock on the same resource held by the same application process. For example, your application reads data which requires an IS lock on a table space. Based on further calculation, the application updates the same data which requires an IX lock on the table space. The application is said to promote the tablespace lock from IS to IX. Now, the effects of this is when promoting the lock, DB2 first waits until any incompatible locks held by other processes are released. When locks are promoted, they are promoted in the direction of increasing control over resources. So, from IS to IX, S to X, IX to SIX or X, from S to X, from U to X, and from SIX to X. So it always promoted to the next increasing control. Escalation. So something's escalating there in that office. A lock escalation is the act of releasing a large number of page, row, lob, or XML locks held by an application process on a single table or tablespace to acquire a table or tablespace lock or set of partition locks of mode S or X instead. So until you reach the lock max parameter, DB2 will acquire locks for each page or row that you're accessing. If you're doing a huge update, DB2 will make the judgment call to say, okay, I'm acquiring too many locks here. I'm acquiring too much storage. I will release all of the locks, free up all that storage, and just have a more restrictive lock on the table space. So that frees up storage, speeds things up, but kicks everybody else out. Lock escalation is suspended during the execution of SQL statements for alter, create, drop, grant, and revoke statements. When it occurs, lock escalation varies by table space depending on the values of lock size and lock max. And as a rough estimate, if 1/4 of your lock escalations cause timeouts or deadlocks, then the escalation is not effective for you. You might alter the table to increase lock max and thus decrease the number of escalations. Alternatively, if lock escalation is a problem, you can use lockmax 0 to disable it. So suspension, there's somebody being suspended from a suspension bridge. An application encounters lock suspension when it requests a lock that is already held by another application process and cannot be shared. The suspended process temporarily stops running. A suspended process resumes when all processes that hold the conflicting lock releases them, or the requesting process experiences a timeout or deadlock and the process resumes and handles an error condition. A timeout. An application process encounters a timeout when it terminates because of a suspension that exceeds a preset interval. DB2 terminates the process, issues a message, and returns an error code. For example, an application process attempts to update a large tablespace that's been reorganized by a reorg tablespace with share level none. It's likely that the utility job does not release the control of the tablespace before the application process times out. Deadlocks. A deadlock occurs when two or more application processes each hold locks on resources that the others need and without which they cannot proceed. After a preset time interval, DB2 rolls back the current unit of work of one of the processes or requests the process to terminate. Now, in determining which processes to roll back or terminate, DB2 assesses many characteristics of the processes that are involved in the deadlock and chooses the one that, if terminated, will cause the least impact relative to the other processes. By choosing a process to roll back or terminate, DB2 frees the locks and allows the remaining processes to continue. So these are your claims, drains, and locks. Let's finish off by touching lightly on what latches are. So a latch, think turnstiles. A latch is a lightweight, short duration synchronization mechanism used by DB2 for internal structures. Unlike locks, latches are for system resources and not data. They're critical for high-speed control of things like buffer pools, index updates, global buffer pools. They always occur within a single subsystem or member. If you need to serialize something across data sharing groups, a global lock will be used. And that's in an X or S state only, and they are typically a very short duration. DB2 acquires the latch, does whatever needs to be done, and then releases it. For example, get a latch for a DB2 storage pool, acquire the storage you need, and then release the latch on the storage pool. If the latch is not available, the request for the latch is queued. And if lots of activity is going on requiring latches, then you get something called latch contention, which can be a serious performance bottleneck. Bart Steegman's presentation on the IDUG content pages contains much more detail that I am prepared to cover in this presentation. So coming towards the end, what happens if your subsystem has performance problems? We go into troubleshooting mode. So you can use your subsystem performance monitors, OmegaMon, BMCs, Broadcom's tools. They detect things like latch contention, lock suspension. You can use application performance monitors to detect and report on deadlocks and timeouts. You can use the -display commands to investigate deadlocks and timeouts with the use or claimers or locks keywords. Make sure your utilities are tuned with the right parameters, particularly share level change reorgs. You can run at any time of day, but so long as the locking requirements are compatible with your SLAs, you can use a delay. You can delay the switch phase to a quiet period, for example, but always use lock avoidance techniques where possible, such as row level locking, uncommitted read isolation levels for read-only transactions, if that's appropriate, and always monitor, measure, tune, and repeat. That basically was it. Claims are polite requests to use the data. They allow concurrency while protecting against chaos. Drains let utilities take over table spaces safely. It's about clearing the way. Locks keep your data safe. They prevent overrides, corruptions, and chaos. Latches keeps DB2 internal operations humming along at lightning speed. They choose the right isolation levels for balances performance and consistency. But monitor, measure, tune, repeat. That was it. I don't think there are any questions.
Just having a look. No questions at the moment. Has anybody got
Session is
any?
9-0. So please give feedback so we can make these sessions better for you in the future. And please click and scan and sign up to the DB2 user group, the UK DB2 user group, join the conversation and keep informed.
Right. Well, thanks very much for that, Marcus. That was brilliant. Lots of detail there on and lots of analogies that explain how these things work and how they look. So I think that's really good picking those out. If you do have any questions, shout now, or I think we'll close for a quick lunch. And then this afternoon restarts at 12:30. Anthony Giappatoni up for DB2. So if there's no more questions, everybody's ducking for lunch by the looks of it, Marcus. So
Yeah.
I think we'll leave it there. Thanks very much, everyone. Thanks,
See you later.
Marcus. Catch you later.